Earth's moon is only natural satellite, a fascinating celestial body with a rich history and unique characteristics. But did you know how Earth's moon formed was? Here, let's find out Earth's moon form. When did the moon form? And what did the early moon look like? Scientists have been proposed several different theories for the moon. The theories that are best supported by all the available data show the moon formed during a giant impact between the proto-Earth and another protoplanet roughly the size of Mars, sometimes called Theia. This moon formed from the impact debris, a mixture of molten rock and hot gas. It is flung out into space by the impact and potentially forming a disk of material that we know as a lunar synestia. This theory refers to samples of rock from the moon, brought to Earth by lunar meteorites and the Apollo moon landings. This can be used to understand the history of the moon and its relationship to the Earth through the chemistry of their minerals. Professor Andy Davis, as planetary scientist in the Geophysical Sciences Department at the University of Chicago, make precise measurements of lunar samples to determine exactly what they're made of, and identify the chemical fingerprints of different geological processes like the melting and mixing of rocks and the evaporation of gases. One of the biggest clues about where the moon came from actually comes from oxygen. Now, oxygen, just like many other elements, can exist in different versions called isotopes. Here's the interesting part. Meteorites from leftover asteroids in our solar system each have their own unique mix of these oxygen isotopes. So, when scientists measure the oxygen isotopes in a planet, they can figure out what kinds of asteroids smashed together to form it. And when they looked at lunar samples, they found the moon's oxygen isotopes are almost identical to Earth's, which tells us the two are closely linked. Some scientists think the moon's oxygen isotopes look so much like Earth's because the planet that collided with us was made of the same mix of meteorites, meaning it probably formed nearby in the solar system. Others argue that after the giant impact, oxygen moved freely in the hot vapor cloud around Earth and the moon, blending everything together and wiping out any differences between Earth and Theia. But here's the twist. The moon's chemistry isn't identical to Earth's. During those extreme impact temperatures, elements we don't usually consider gases, like potassium, zinc, and sodium, can vaporize. And when we check lunar rocks, they're missing much of these volatile elements compared to Earth's rocks. One idea is that after the giant impact, the hot debris cloud had plenty of time to let certain elements evaporate before it came together to form the moon. Another possibility is that the moon itself started off blazing hot, with a deep magma ocean like Earth's. But because the moon has weaker gravity and no atmosphere, volatile elements that would normally stay trapped in a bigger planet could just escape into space. Both scenarios are tough to explain without a massive impact. That kind of collision would generate the extreme heat needed to account for the missing potassium, zinc, and sodium we see in lunar rocks. And it would also allow lots of mixing between early Earth and the material that became the moon. The big question is, when exactly did this impact happen? Scientists think the moon was born from a giant impact, somewhere between 60 and 175 million years after the solar system first formed. How do they figure that out? By studying Earth's rocks. As early planetesimals grew, they heated up, thanks to constant collisions and the radioactive decay inside their minerals. That heat was enough to melt them, letting heavy metals like iron and nickel sink inward to form a core, while lighter rocks floated to the surface. This process helps scientists trace back when the moon's formation likely happened. By the time the moon-forming impact happened, Earth had already split into rock and metal layers. But that massive collision remelted the planet, mixing those layers back together. Afterwards, Earth was still hot enough to separate again into fresh rock and metal layers. And that's the key scientists used to figure out when the moon formed. Here's how. When rock and metal mix, they swap certain elements. Hafnium, for example, prefers to stay in rock, while tungsten prefers metal. Hafnium slowly decays into tungsten over about 10 million years. Early in Earth's history, there was plenty of hafnium in the rocky layer because it hadn't yet decayed. But by the time of the moon-forming impact, much of that hafnium had already turned into tungsten. When the Earth remixed, the new tungsten sank into the core, leaving the outer rocky layer with less hafnium and the core enriched with tungsten. That chemical fingerprint is what helps scientists date the moon's birth. Today, all the hafnium is gone. It's half. Life is short compared to Earth's age. But that's actually useful, because it lets scientists piece together what happened in the first 100 million years of the solar system. The amount of tungsten in Earth's rocks depends on when the planet last separated into rock and metal layers. And here's the catch. The tungsten levels are too low to be explained by an early separation alone. Something must have remixed Earth's layers. The best explanation? A colossal impact, about 60 to 175 million years after the solar system was born. Most of us imagine the moon as a dull, gray world covered in craters. But for much of its history, it was surprisingly active. Like Earth, the moon began with a thick ocean of molten rock on its surface. Unlike Earth, though, it never developed tectonic plates. Instead, its surface solidified into a thick crust, made mostly of a pale mineral called feldspar. That's what gives the lunar highlands their bright appearance. Feldspar floated to the top as the magma ocean cooled, creating a unique crust that scientists used to study how the moon's chemistry and cooling differed from Earth's. But the story doesn't end there. Heat left over from the giant impact, plus radioactive elements inside, melted rock deep below the surface, fueling volcanic eruptions. These eruptions produced dark basalt, the same kind of rock you see at volcanoes in Hawaii or Iceland. The lava spread across vast areas, forming the lunar mare, or seas up to a mile thick. Today, those dark patches cover about 16% of the moon's surface and are visible to the naked eye. Scientists can tell that the moon's dark basalt plains, called mare, are younger than its bright feldspar highlands by counting craters. The mare have fewer craters, meaning they've had less time to be bombarded. In fact, the youngest mare are only about 1.1 billion years old, proof that volcanoes were still erupting on the moon long after life had already begun on Earth. Another fascinating clue comes from the moon's orbit. Today, it drifts about 1.5 inches farther away from Earth each year. But when scientists run the clock backwards, they find the moon was once 17 times closer, just 14,000 miles away compared to the 250,000 miles we see now. That changing distance is critical. It tells us something about the giant impact that formed the moon, because the size, speed, and angle of the colliding bodies all affect the orbit of the Earth-Moon system. To solve the mystery, scientists need impact simulations that match not only the moon's chemistry, but also its original orbit and spin. The questions remain. Scientists still debate about the details of impact, although agree that moon formed of an impact. Some scientists even argue that multiple impacts might have formed the moon, instead of just one. So, to measure the theories about how Earth's moon formed, new samples from the moon are needed. Of course, it needs to future exploration.